I'm Ryan Urbanowitz, and this is Part 3B of Machine Learning Essentials for Biomedical Data Science. In this next video on data preparation, we'll cover data splitting and feature processing. Here's a quick reminder of the parts making up this video series. In our last video, we covered the first half of our data preparation section, with focus on exploratory analysis and data wrangling. So now we're moving on from data wrangling to discuss data splitting, another key aspect of data preparation. Data splitting refers to the partitioning of available data into two or more parts. The most fundamental form of data splitting involves partitioning data into training and testing sets. The training partition includes the instances that will be used to train a predictive model, and the testing partition includes the instances that will be used to evaluate the model's performance on data that it previously has not seen. So at what point in data preparation do we want to split the data? This can vary slightly from one analysis to another, depending on what data preparation elements are being utilized. However, the key factor here is to conduct data splitting before any other step where there is the potential to learn from instances that might end up in the testing partition. So certainly, you'll want to split your data prior to modeling, but also you'll ideally want to split prior to most any feature processing, with the notable exception of feature engineering, which typically uses outside expert knowledge rather than information from the data itself, as we'll discuss later in this video. Further, you'll want to split prior to imputation if you've decided to impute the missing values in your data. When it comes to data splitting, you may be wondering what proportion of instances to hold out for a test set. There isn't any hard and fast rule for this. However, you should use at least half of the data for training. The most common split ratios are 80% to 20 or 70% to 30, and one of the most strongly recommended ratios is 90% to 10, as we'll see later. In determining this split, you should take the total number of instances you have into consideration, where the more instances you have, generally the smaller a proportion of them can be left out for testing, while ensuring that you still have a sufficient number of testing instances to get a good evaluation of your model. Considering the argument for choosing a larger testing instance holdout, if you had only 100 instances in total, and you chose a 90% to 10% split, you'd only have 10 instances for model evaluation. This would likely increase the chance of sample bias, which we'll talk about more in a few slides. Conversely, we have the argument for choosing a smaller testing holdout. Specifically, this will leave a larger number of training instances for model training, which typically promotes improved model training. Data splitting allows us to account for one of the biggest concerns and pitfalls in machine learning, and that's overfitting. Overfitting is the fitting of a model exactly to the training data, or at least moving in that direction. In other words, overfitting is memorizing patterns in the training data rather than learning generalizable associations that'll still be useful to new data we haven't seen yet. Let's look at some specific examples. Here we have modeling taking place both in classification and regression datasets. An ideal model, represented by the solid or dashed lines, will yield both low training error and low testing error. If the model is overfit, often it is overly complex, and while it achieves low training error, it often will yield high testing error, meaning that it poorly generalizes. Conversely, if the model is underfit, it is often overly simplistic and yields both a high training error and high testing error. Next, let's consider another level of data splitting, specifically further splitting the training partition into a training and validation dataset. Validation data are instances used to provide an unbiased evaluation of a model fit on the training data while tuning an algorithm's hyperparameters. Again, hyperparameters are the algorithm settings that control how that algorithm operates. In this figure, we have the original dataset first being split into a training and testing set, and next the training set is subsequently partitioned further into a training and validation set. At this point, we can train a model using some initial hyperparameter values and evaluate the model performance immediately using this validation set. This can be repeated many times, testing out model performance when trained with different hyperparameter settings, with the aim of optimizing the model. This way, we still have a holdout test set available to conduct a final evaluation of the model once we've selected what we believe to be the optimal algorithm hyperparameter settings. Of note, the terms validation data and testing data are often confusingly used by practitioners and in the literature interchangeably. However, these terms are most often used in the way that I'm defining them here. Also of note, when validation is used repeatedly to optimize algorithm hyperparameters, our model evaluation using the validation data becomes more biased with each subsequent use. This is because the experience on validation data eventually gets indirectly incorporated into the model. Again, this emphasizes the importance of retaining a holdout test set for a final model evaluation. Of note, the same concern regarding increasing bias occurs when using the same validation set repeatedly to optimize feature selection. At this point, let's stop and discuss another machine learning pitfall, specifically sample bias. In the context of modeling, sample bias refers to the bias in model evaluation that can occur if the training or testing data was not truly representative of the population. Recall that when we collect data from a target population, let's say Alzheimer's patients, since it's impractical, if not impossible, to collect data from the entire population, we sample an instance subset from the population for our analysis. Ideally, we want our sample to be as representative of the larger population as possible. However, this can be very difficult to do as well, and we should generally assume that there is at least some level of sample bias in our data. Here, we're going to consider two specific scenarios in which sample bias can impact our machine learning analysis. The first occurs during data collection. In this scenario, as we sample from the population, we might be selecting a less representative set of instances, either due to random chance, which is largely unavoidable, or also perhaps due to some form of selection bias. For example, we pick patients that tend to have a less severe form of a target disease because patients that had the more severe form are more likely to be deceased, and thus are less frequent in the population. Or perhaps the sample was taken in a location inhabited mainly by a given race, leading to a racially biased sample when the analysis is applied to a broader set of peoples. Ultimately, this type of sample bias can result in a model that poorly generalizes in practice. Another scenario to consider is with respect to data splitting. While the splitting of data into training, validation, and testing partitions is a good start, it has one glaring limitation. And this has to do with which of the instances happens to end up being randomly included in the different partitions. When data is split only once, it's quite possible that either the training, testing, or both partitions may not be representative of either the original sample or the original population as a whole. As a rough example, imagine that 20% of your original sample have a clear, simple relationship between features and outcome. If by chance most of these ended up in the training partition, but not the testing partition, the model might achieve higher training accuracy, but lower testing accuracy, leading us to underestimate the quality of the model. Instead, if more of these simple examples had ended up in the testing data, we might have observed lower training accuracy and higher testing accuracy, leading us to overestimate the quality of the model. On the next slide, we will discuss a commonly used strategy to help us account for this second scenario of sample bias. Okay, so to help address sample bias in data partitioning, as well as to evaluate consistency in modeling, it's typical to employ k-fold cross-validation as a more comprehensive approach to data splitting. K-fold cross-validation is a resampling procedure used to evaluate machine learning models on a limited data sample. Again, we do this primarily to address the risk of sample bias in data splitting. And how does this work? Well, given our original sample of data instances represented by this blue box, we begin by randomly shuffling them. Next, we randomly split the instances of this data into some number of folds, represented here by the variable k. For example, here we're conducting 5-fold cross-validation. Next, for each fold, we're going to take the current fold as the test data, and the combination of the remaining folds as the training set. Next, we're going to fit a model on the respective training set and evaluate it with the respective holdout testing set. And you can see we do this for each split, where the number of folds determines the number of data splits, and subsequently, the number of models that will be trained. This way, every instance in the original dataset gets to participate as both a training and testing instance in the overall analysis. Lastly, we summarize the machine learning algorithm's holdout performance on the data, averaged across the k folds. We can examine model performance consistency across those splits to get a better sense of the impact of sample bias when splitting. and the average model performance offers a fairer, less biased way of comparing algorithm performance on a given dataset. Now let's look further at some practical aspects of using k-fold cross-validation. First off, when do we employ it? First, it can be employed globally in the analysis pipeline, as we just illustrated, yielding multiple trained models to more fairly evaluate and compare algorithm performance. Furthermore, k-fold cross-validation is often employed specifically for hyperparameter optimization. Here, the study-level training data is further partitioned into further training and validation splits. This is done in order to try out different hyperparameter settings prior to training a final model. However, the models trained in hyperparameter optimization are temporary and are discarded after being evaluated. As a quick side note, in an analysis, it's often best practice to employ cross-validation both globally and for hyperparameter optimization. As we'll see later, this variation of cross-validation is also known as nested cross-validation. Next, we have the question of how to choose the value of k, noting the immediate drawback that a higher number of splits will require more computing time. First, a solid go-to is to set k to 10 partitions. Previous empirical work has suggested that 10 splits generally yields low bias and only modest variance in model skill evaluations. A k of 5, which yields an 80% to 20% ratio of training to testing data, is also commonly used. Alternatively, practitioners can go out of their way to select a k such that each train and test partition is statistically representative of the data as a whole. And on the extreme end, practitioners can employ leave one out cross-validation, where k is set to the number of instances in the data. While this is likely to yield the most accurate model skill estimate, it obviously will take the most compute time by far and is often impractical. Lastly, on the topic of cross-validation, let's cover some of its major variations. The first is stratified cross-validation. This approach seeks to ensure that some aspect of the original data is preserved within each of the respective partitions. In classification problems, this is most commonly used to ensure that the class balance, in other words, case control balance, in each partition is as close as possible to the original data's balance. Furthermore, this could be done to ensure that the distribution of values for some key feature in the dataset is preserved from one partition to the next. For example, maybe to ensure that a similar proportion of males and females are included within each partition. The second variation is matched cross-validation. This is preferable to employ when working with data that's been collected in a way that matches cases and controls based on some known covariate or covariates. For example, when collecting samples for an Alzheimer's study, we may want to account for the known covariate of patient age. And to do so, we just add case and control samples in pairs, each with the same or similar age value. This pre-adjusts the data in an attempt to remove the effect of the known covariate. And when it comes to cross-validation, it's important to keep those matched instances together within the same partition. The third variation is repeated crossover. This simply seeks to provide even more rigor and reliability to the analysis by repeating the cross-validation procedure some n number of times, with the original data reshuffled prior to each repetition. And lastly, the fourth variation we mentioned earlier, specifically nested cross-validation. This is where cross-validation is secondarily employed within the training partition of a primary cross-validation split. As mentioned, this is commonly done to evaluate models at the primary level and to evaluate hyperparameter optimization at the secondary level. Alright, so now we're moving on to the last part of our discussion of data preparation, and that's feature processing. As part of data preparation, feature processing is all about improving the data representation so that machine learning modeling can achieve higher performance during training. I'll quickly review the elements of feature processing that we'll cover, and then go into further detail on each in subsequent slides. So first off, there's feature engineering, which has already been mentioned a few times in this video series. Feature engineering uses knowledge about the dataset problem domain to build new features from existing ones. Second, there's feature learning. This element is an automatic analog to feature engineering, where we can apply various methods to automatically build new features from existing ones. Third, there's feature transformation. This seeks to change the scale or distribution of feature values across features. Fourth, there's dimensionality reduction. which seeks to create a compact projection of features from a higher to lower dimensionality. And lastly, there's feature selection. This critical element seeks to remove irrelevant or redundant features from the dataset. Notably, feature selection can be accomplished during either data pre-processing or during modeling itself. Let's start by looking more closely at feature engineering. As we mentioned before, this is where a practitioner leverages their domain knowledge to build new features from existing ones. Typically, this differs from feature extraction, in that feature engineering creates new features from ones in the raw data that we could have used directly for machine learning. In other words, it works with structured data that is already likely in tabular data format. As mentioned, feature engineering can be conducted before data splitting, since domain knowledge rather than the values of the data itself are being used to create new features. Notably, the term feature engineering is sometimes used more generally to refer to all aspects of feature processing, with the exception of feature selection, as well as to both feature extraction and data formatting. So be mindful of how this term is being used in different contexts. Given that data science is a rapidly developing field, often investigators will have their own understandings and perspectives on how to use many of the terms we cover in this video series. Now let's briefly summarize the process used to engineer features. First, do some brainstorming and testing of candidate features based on your understanding of the data and problem domain. Second, decide what features you want to create for the final dataset and add them. Third, you can test the impact of these engineered features on machine learning modeling. In other words, do they help improve performance? And lastly, you can improve your engineered feature as needed and then repeat. Let's look at some specific examples of feature engineering. We saw this example before, but if you have start and stop time points in your data, let's say for the administration of some treatment, this could be engineered into a single treatment duration feature. Or, as we discussed earlier, if we have a categorical feature, we could employ one-hot encoding. We could re-encode the feature as a set of other true-false features to ensure that any downstream modeling indeed treats that feature as categorical. Furthermore, for continuous features, we can encode bins of value ranges. This can be useful in specific situations. However, this type of data encoding is also likely to lead to some lost information. Notably, this type of encoding can also be used to transform a quantitative outcome into a binary or multi-class outcome. However, this can similarly lead to a loss of information. Another example is to transform a feature from one set of coordinates to another. For example, from coordinate system to polar coordinates, which can be important for getting a simple machine learning algorithm to effectively model that feature's ability to predict outcome. In this example, the distinction between feature engineering and feature transformation, which we'll talk about a bit more later, gets fuzzy. And one further example, if we have a feature with a reasonably high frequency of missing values, we can actually engineer a feature that encodes the missingness of that feature as a potentially predictive binary feature. For example, perhaps we're studying alcoholism, and in a patient's survey, it might turn out that a patient's willingness to include an answer about whether or not they consider themselves to be an alcoholic is in itself predictive of whether they are an alcoholic. Engineering missingness features can be potentially predictive, except in the case of features that are MCAR, or missing completely at random. So this brings up another potential machine learning pitfall, and that is understanding the types of missing data that are possible. The first of these is missing completely at random, or MCAR, which we just mentioned. This is missingness that is completely unrelated to other information in the data. The implication here is that it's safe to remove instances with missing values in this feature, as it should not result in any biasing of the remaining data. The second type of missingness is missing at random, or MAR. In this case, for all intents and purposes, we can still consider missingness to be random in the study. However, it's possible to predict the value of missing values based on other available data, with a higher degree of certainty than random chance. The implication here is that we can impute missing values or encode missingness as an engineered feature. These first two types of missingness are considered to be ignorable at the study level. And lastly, we have missing not at random, or MNAR. In this case, it should be possible to predict the value of missing values based on data that isn't currently available. In other words, perhaps it didn't happen to be collected by the researcher, or perhaps it was impossible to collect. This type of missingness is most dangerous within a study and is not ignorable. Ideally, a researcher should seek to obtain those missing values or understand the specific reasons for its missingness before drawing conclusions or putting a model trained on this data into practice. Now we move on to our next element of feature processing, and that's feature learning. Feature learning is similar in spirit to feature engineering, but automatically creates new features using existing features in the data with the goal of facilitating or improving downstream modeling. Feature learning can also be referred to as feature construction, and again is often lumped in under the name feature engineering. Feature learning typically involves the application of machine learning strategy to test and evaluate ways to combine and transform two or more features from the original dataset. Often, there's a fine line between feature learning and machine learning modeling itself. Typically, this distinction is dependent on how the output is used. In other words, whether the output determines the value of a newly constructed feature that's fed into downstream modeling, or if the output is used to make predictions as a model. Now let's take a look at some specific examples. Notably, there are many strategies out there, and the three I'll mention here were developed by myself or colleagues. One example is multi-factor dimensionality reduction, or MDR, developed by Ritchie, Moore, and others. MDR takes two or more features and combines them into one in order to explicitly detect feature interactions. Two other examples include FEW and FEAT, developed by LaCava and Moore, which uses genetic programming to evolve new features based on the mathematical combination of existing features in the dataset. And lastly, there's RARE and FIBRS, two related algorithms developed by Desariaju and myself to evolve bins of features to capture rare, additive, or heterogeneous associations involving two or more existing features. Let's briefly look a bit more at binning as a form of feature learning. In the context of genomic analyses, many genetic features can have rare feature states. This presents challenges for statistical analysis and machine learning, as this rarity limits the power of these methods to detect true associations. Binning has often been used in such problems to try and improve power to detect the impact of rare variants by combining rare features within a genetic region to yield a single variable, also known as a bin. As shown here, experts might identify specific genomic regions based on their domain knowledge and then count the number of rare variants found in a subject within each of these regions. Thus, technically, this type of binning is an example of feature engineering. Researchers can then evaluate the bin's association with outcome, where the bin is a new feature in the dataset. Most binning methods rely on assumptions made about the domain, for example, what spatial region of the genome to designate as a bin. And often these binning methods don't account for the directionality of rare variant effects. In other words, does an individual variant increase or decrease the risk of a given disease outcome? This is an example of where feature learning methods, like RARE and FIBRS, mentioned in the last slide, can be advantageous over feature engineering approaches, in particular when our domain expertise is based on incorrect assumptions or biases. Next, we move on to our third element of feature processing, specifically feature transformation. Feature transformation seeks to change the scale or distribution of features in the data by applying some form of mathematical transformation. Fundamentally, this transforms the relationship of an independent feature with a dependent variable. Also, as mentioned earlier, there is some overlap here with feature engineering, as feature transformation can be achieved with or without the use of domain knowledge. There are generally two goals in feature transformation. The first is to change the distribution of a given feature. This transforms the values of the feature such that it follows a new probability distribution. We can see some specific examples of well-recognized value distributions here on the right, including binomial, exponential, and normal or Gaussian distributions, to call out a few. Changing the distribution of a feature can help to linearize a feature's association with outcome, making the relationship easier to model for simpler machine learning methodologies. Another goal of feature transformation is scaling. Here, the goal is simply to transform all feature values so they fit within a specific scale, for example, between the values of 0 and 1 or 0 and 100. Let's take a closer look at scaling as a goal of feature transformation. So first off, why can feature scaling be an important consideration? In short, some machine learning algorithms require scaling in order to perform properly or optimally. These include algorithms such as principal component analysis, which we'll talk about more in a couple of slides. Also, algorithms that use gradient descent for parameter optimization, for example, linear logistic regression and neural networks. And also distance-based algorithms, such as k-nearest neighbors, k-means, and support vector machines. If you plan to use any of these algorithms, you'll want to scale your features prior to applying these methods. It's useful to note that data scaling shouldn't hurt the performance of other machine learning algorithms, even if they don't require it. However, if you do scale your data, you will need to make sure to scale any future data in the same way prior to applying any trained model to it. Further, when it comes to model interpretation or explanation, which we'll discuss in a later video, you'll need to remember that your model assumes that the features have been scaled, so that you know how to properly interpret the model downstream. When it comes to scaling, there are two major approaches. The first is normalization, where values are shifted and rescaled so they end up ranging between 0 and 1. In these box plots, we can see 4 original features in the dataset and their respective value ranges before and after normalization. Note that after normalization, each of these features has a value between 0 and 1. Normalization is particularly useful on features without a Gaussian distribution. And it's also useful when you'll use algorithms that don't assume any data distribution, for example, k-nearest neighbors or neural networks. Another scaling approach is standardization, where feature values are centered around the mean with a unit standard deviation. On the right, we can see the same set of features following standardization. Notice here that our means are centered around 0. Standardization is particularly useful on features with values that follow a Gaussian distribution, but this is not necessary for standardization to be applied. Moving on to our next feature processing element, we have dimensionality reduction. Dimensionality reduction creates compact projections of features in the data. It does this by transforming data from a high-dimensional space to a low-dimensional space, often with the goal of reducing the number of features to analyze in a dataset. Dimensionality reduction helps to address the curse of dimensionality, which we talked about in our second video covering biomedical data. Dimensionality reduction methods can be broadly divided into linear and nonlinear approaches, where the latter are indicated in this figure by stars. The majority of these methods are unsupervised learning approaches, meaning they operate on the features only and don't require an outcome label. One notable exception is the dimensionality reduction method called linear discriminant analysis, or LDA, which is a supervised learning approach. Of these methods, probably the best known is PCA, or principal component analysis. Let's briefly review principal component analysis as a dimensionality reduction strategy. PCA projects the dataset feature space into principal components that capture the maximum variation and minimum error. Let's take a look at how principal components are identified from the data. Let's say that we have an n-dimensional dataset where n is the number of features. For simplicity, we'll illustrate this data space in 2 dimensions, as seen here. To find the first principal component, or PC1, we seek to identify a line anchored at the center of our n-dimensional data cloud that's rotated in n-dimensional space. This line here mirrors the data point projections. We can see these projections as red dots connected with dotted red lines to their original data points. This process stops when the total distance among the projected points is maximized on the line, as we'll see here in just a second. Right there. And at the same time, when the error, or sum of the dotted red line lengths, is minimized. This is the first principal component, which is the line that captures the maximum variation across features of the dataset as a whole. The second principal component, or PC2, is a line that's orthogonal to PC1 in n-dimensional space that captures the second most variation in the dataset. We can see principal components 1 and 2 in this figure, illustrating gene expression of 2 different genes across a set of patients. While it is possible for principal component analysis to help separate out outcomes, since this is unsupervised learning, there's no guarantee or even a strong expectation that principal component features will be more predictive of outcome. Also of note, since principal components are a complex combination of information across many or all features in the dataset, Relying on such features in modeling can make model interpretation and explanation much more difficult, since the contribution of original features has been obscured within these principal components. Since we're on the topic of unsupervised machine learning methods, here's a listing of such methods grouped as either being dimensionality reduction, deep learning, clustering, instance-based methods, or rule-based methods. On whole, unsupervised learning algorithms can be useful for exploratory analysis, data cleaning, feature extraction, or dimensionality reduction. The last element of feature processing and data preparation as a whole is feature selection. Feature selection refers to the removal of irrelevant or highly correlated, in other words, redundant, features in the dataset in order to reduce the size of the feature space that will need to be explored during modeling. Feature selection can be applied to all original features, as well as all new ones introduced during feature processing. In other words, features created in feature engineering, feature learning, or dimensionality reduction. This aspect of data processing is valuable in reducing the downstream computational burden of modeling, in particular in datasets with a very large number of features. Furthermore, it's helping to reduce the data noise that's been added by the presence of irrelevant features, which can slow or prevent successful modeling. Feature selection can be accomplished in a number of ways. First, it can be achieved manually using domain knowledge to remove features that are known to be irrelevant or that are not wanted in the trained model. Alternatively, the decision to keep each feature could be made via the application of a simple test of association with outcome. However, this may be too oversimplistic of an approach when the data includes complex multivariate associations. And lastly, feature selection can be accomplished using machine learning, which we'll discuss more in the next couple of slides. One of the simplest things to target in feature selection is the removal of redundant features using unsupervised learning methods. Specifically here, we typically evaluate feature correlation, which is a bivariate analysis measuring the strength of association between two variables and the direction of this relationship. Specific examples include Pearson, Kendall, and Spearman correlation. On the right, we have a feature correlation heat map, which we've seen before, commonly used to visualize correlated features in data. Back in data wrangling, data cleaning should have already addressed the removal of all but one feature in a pair or group of 100% correlated features. Keeping a record of these correlations can help to identify the broader set of features that represent candidates for causing the observed outcome, rather than features that are just associated with outcome. But beyond perfectly correlated features, we can also consider removing highly correlated features. For example, features with greater than 90% correlation. Often, highly correlated features can simply capture redundant information that can be safely removed from the data. However, it should be noted that it is possible for critical information to be lost in the process of removing highly correlated features, such as illustrated on this example on the right. This scatter plot illustrates the values of two features on the y and x axes, respectively, and it shows the binary outcome of data points represented as either blue or red dots. We can see from this figure that the two features are highly correlated with one another. However, if we were to remove one of these two features, we would entirely lose the ability to effectively differentiate between the blue and red outcomes. And this is because there's clearly an interaction between these features that's strongly predictive of outcome. Most feature selection methods actually focus on removing irrelevant rather than redundant features. However, notably, there are some methods that can do both at once. On this slide, let's discuss the typical families of supervised learning feature selection approaches. Firstly, there are filter methods. Filter methods estimate proxy measures for each feature in order to rank them. After ranking, the user can decide how many of these top features to select or discard. Filter methods are fast and operate independent of a modeling algorithm, meaning that the same filter-based feature selection could be applied unbiased by the specific strengths or weaknesses of a given modeling algorithm. Examples of filter methods include mutual information and measures of correlation between feature and outcome pairs. The second family of feature selection methods are wrapper methods. These methods test feature subsets using machine learning modeling, removing features by trial and error. Wrapper methods are computationally expensive. They scale poorly as datasets become larger, and they're susceptible and biased to the assumptions being made by the machine learning algorithm used by the wrapper. Specific examples of wrapper methods include recursive feature elimination and genetic algorithms. The last feature selection family we'll review are embedded, aka intrinsic, methods. Here, feature selection is integrated alongside of modeling. Embedded methods are generally less computationally expensive and less prone to overfitting than wrapper methods, but they're more expensive than filter methods. However, like wrapper methods, they're also biased by the assumptions of the machine learning algorithm being used. Specific examples of embedded methods include L1 lasso regression and decision trees. Technically, many machine learning algorithms can be considered to be embedded feature selection methods, since many machine learning algorithms can choose what features end up in the final model. Let's briefly take a closer look at filter-based feature selection methods. Here's a list including some additional example methods, with mutual information illustrated on the right. Note that most filter-based feature selection methods are only capable of detecting simple univariate associations. However, there is one group of filter-based feature selection methods, called relief-based algorithms, that are uniquely sensitive to both univariate associations as well as multivariate feature interactions. Personally, I'm a big fan of relief-based algorithms, abbreviated here as RBAs. And full disclosure, over the next few slides, I'm going to discuss some of our own research and associated software that we've developed to improve and make these methods more easily accessible. First, let me give you some basic intuition as to how RBAs work. These methods start by calculating the distances between all instance pairs in the data in order to identify neighbors for each. Next, as illustrated in this figure, for each instance in the dataset, labeled in this figure as the target instance, we compare the values for all features between the target and neighboring hits, which are neighboring instances with the same class as the target, and between the target and neighboring misses, which are neighboring instances with a different class. Next, we go through all features and scan for value differences. When we encounter them in a hit, we subtract from that feature's score, since we know that that feature value difference alone did not lead to a different outcome. When we encounter a feature value difference in a miss, we add to that feature's score, since we have new evidence that that feature's value difference might be associated with the observed outcome difference. This set of scoring updates happens for all instances in the dataset, with the RBA ultimately outputting a list of features ranked by their relief score. This procedure may seem extremely simple and well suited for detecting simple univariate associations. However, the key to its ability to also detect feature interactions is that these scoring updates only occurs between neighboring pairs of instances, and not between all pairs of instances. To be clear, no model is generated by the RBA. Myself and colleagues have previously written this detailed introduction and review of these unique algorithms. Now let's briefly review some of the key advantages and disadvantages of relief-based algorithms. Under advantages, relief-based algorithms can reliably detect 2- and 3-way interaction effects without requiring exhaustive search of feature combinations. In other words, RBAs scale linearly with the number of features in your data for detecting interactions. This alone is a pretty major advantage when it comes to detecting feature interactions with any methodology. Second, as a filter-based method, RBAs can be combined with any downstream modeling algorithm, so that prior feature selection hasn't been based on the assumptions made by any single modeling algorithm. And lastly, RBA feature scores can also be used to guide the machine learning modeling itself by prioritizing the features with the highest scores as a source of statistical expert knowledge. However, in terms of disadvantages, RBAs scale quadratically with the number of training instances. This is because we must calculate the distances between all instance pairs. However, this computational burden can be lessened by randomly sampling an instance subset for the purpose of running an RBA. Furthermore, RBAs do not explicitly indicate which features are interacting with which other ones. They only provide a way to more confidently filter out features that are likely to be irrelevant even in the context of there being feature interactions. As a touch of shameless self-promotion, if you're interested in using or learning more about RBAs, check out this 2018 paper on benchmarking relief-based feature selection methods. You can also easily install ReBATE, the scikit-learn compatible suite of RBA algorithms illustrated on this slide. One final caveat to using RBAs is how they perform on very large feature spaces. In the aforementioned benchmarking paper, we showed that the ability of these methods to detect pure two-way interactions deteriorated in datasets with between 10,000 and 100,000 features and beyond. Pure interactions refer to feature interactions where each interacting feature has no detectable univariate association with outcome on its own, making them particularly difficult to detect. The heat maps on the right illustrate experiments in simulated datasets with an increasing number of features in the data, the different algorithms tested showed on the y-axis, and the frequency of truly predictive features being ranked above all others on the x-axis. The top row of each heat map is a random shuffle of the features serving as a negative control. The 5 algorithms below it represent a sampling of other commonly used filter and wrapper feature selection algorithms. And the bottom 8 rows are different RBA variations implemented in the aforementioned ReBATE package. Here, a solid dark blue horizontal line for an algorithm indicates that it perfectly prioritized the relevant interacting features above all other features in each of 30 replicate trials conducted. So for 100 features, all algorithms except chi-square, ANOVA, and mutual information detected the pure two-way interactions perfectly. At 1,000 features, the extra tree wrapper algorithms based on decision trees started to fail. And at 10,000 features, the only reliable algorithms are the relief-based ones. And lastly, at 100,000 features, RBAs tended to rank the relevant interacting features only in the top half of all features. However, fortunately, a handful of wrapper methods have been developed that can address this limitation. One such example is TURF, developed by Dr. Jason Moore, which iteratively applies a relief algorithm to the data, each time eliminating some bottom percent of features from consideration in order to ultimately yield a higher quality feature ranking on the remainder. At this point, we've covered the major elements of preparing data as reviewed by this schematic. In subsequent videos, we'll move on to cover the remainder of the elements included in a data science pipeline with machine learning. Thank you for joining me for Part 3B of Machine Learning Essentials for Biomedical Data Science. In the next video, we're going to cover the elements involved in machine learning modeling. If you enjoyed this video, please like and subscribe to follow my future content.